Hello guys, this is Paul McWhorter from TopTechBoy.com, and we are here today with lesson number 9 in our new, in our exciting, in our improved Arduino tutorial series. And what we are going to talk about today is we're going to talk about Ohm's Law and simple circuit analysis. So I need you to pour yourself a nice big mug of iced coffee. No sugar, just black coffee over ice. It's both delicious and refreshing. So get that poured. I need you to get out your Elegoo Super Starter Kit Uno R3 project kit. If you don't have one yet, look in the link down below, hook a brother up, order it from there, and then you can play along at home as well. And so we today are going to be looking at how to do simple circuit design, how to do simple circuit analysis based on Ohm's Law. Now I know what you're thinking. You're thinking, why do I need to know that? Because I am already building circuits as illustrated in some of our earlier projects where we used this this circuit. We built it, made an LED blink. Well, let me tell you why. Because I gave you this circuit, and the reason I was able to give you this circuit is because I used Ohm's Law and I did circuit analysis, and then you just copied what I did. Well, you said, you're probably saying I'm perfectly fine copying what you did. Yeah, but I will not always be here for you. And so you need to know how to do it yourself so that you can make things like this work. So let's talk about, what do I mean by circuit analysis? Well, if I just came in and had you hook the 5 volts directly across the LED, you would get a very large current and your LED would burn very brightly for a short period of time, and then poof, smoke would come out and the LED would be destroyed. On the other hand, if I use too large of a resistor, then you would limit the current too much and either the LED would not turn on or the LED would be very dim. So too small of a resistor, you burn the LED out. Too large of a resistor and the LED burns dimly. And so if you want to make simple projects like this work, you need to know how to do circuit analysis. And so that is what we are going to do today. And the good news is it really is pretty simple. And so let me kind of show you, and we'll go through a circuit analysis together, and then I will have you do some on your own. But let's start with the simplest one possible, something just really simple where we have a voltage supply, and then we come across and we have one resistor. All right, and so this is even simpler than this one was because we just have the voltage supply and the resistor. And let's go ahead and call this R, and then let's call this V. Now, in the example we did earlier, we had R was 330 ohms, but here I'm just going to leave you more generally a voltage applied across a resistor. How do I know what current is going to flow? Well, the voltage, if you think of like a water system, the voltage is kind of like pressure, and the current is kind of like the water flow. But instead of flowing water, we have flowing electrons. And so I know that a water example is not exactly perfect, but you could kind of think of it as this voltage supply is sort of like a pump. And the higher the pressure, it's kind of like a higher voltage. And the higher the pressure, the more water is going to flow. Well, the higher the voltage, the more current is going to flow. And this resistor, that's something that restricts the flow. So it would be something like an obstruction in your pipe. And the larger the obstruction, the smaller the current is going to flow. So it's sort of very similar here. The larger the voltage, the larger the current, and then the larger the resistance, the smaller the current, because that's resisting currents. Because it's sort of like voltage and resistance are fighting against each other. One thing that I need to say, current is the flow of electrons, but it's this quirky little thing that it's in the opposite direction. If you think about, like, if you had an electron here, like charges repel, and so this negative electrode is going to be pushing the electron around this way, and then the electron is going to be attracted to the positive terminal because opposite charges attract. So the kind of quirky thing is the electrons are actually flowing this way, but the current is flowing this way. So current flow, the positive current, is in the opposite direction of the actual flow of the electrons. You really don't have to even think about the flow of the electrons, and so I don't even think about this. I just know that the current comes out of the positive terminal of the battery, and that is a particularly ugly circuit, and so I am going to move to a new sheet of paper. And let me see if I can draw it neater. I wish I could really draw good, but I can't. So that's plus, minus, come down like this. This is voltage. We have current, and my hand is always in your way, isn't it? And we have resistance. Well, we have, to help us with this, we have what is called Ohm's Law. And what does Ohm's Law say? Well, Ohm's Law says the voltage is equal to the current times the resistance. So the voltage here is equal to the current times the resistance. We need to know that V, voltage, is measured in what? Volts. And you're familiar with volts, right? Like maybe you have a 9-volt battery or something like that. You're familiar with that. All right, I, current, is measured in amps. And then R, resistance, is measured in ohms, which is this symbol, and sometimes is called ohms. Now, circuit analysis is really simple for little things like this, but what you have to see is you are rarely going to be given the current and the resistance and calculate the voltage. More likely, let's say that you would be given the voltage and you would be given the resistance and you want to calculate the current. Well, if you have voltage and resistance and want to calculate the current, what could you do to this? You could divide both sides by R. And if you divide, let me say this is the first Ohm's law. If you divide both sides by R, you could say that I is equal to V over R. This is the second form of Ohm's law. And this one you actually kind of use more often, that you have a voltage. A lot of times it might be 5 volts, and then you are given a certain resistor, and then you want to know what current would flow through. That's the second way. Well, what if you had a voltage and you had a desired current and you want the resistor that would give you that current? Well, you could say, you could divide on V equal IR, you could divide both sides by I, and then you could say R is equal to V over I. And so these are 3 ways of writing Ohm's law. They're all equivalent, but what you want to do is you want to pick the one that matches the problem that you have. And so let's just come up with a problem here, okay? And man, I'm going to try so hard to draw a neat one. Okay. So let's say this R is equal to 330 ohms, and this is 5 volts. Okay, so I have 5 volts across 330 ohms. The question is, what is the current? Well, the current, I would use this equation, is equal to V over R, which, what's my voltage? 5 volts over the resistance is 330 ohms. And then I get out my nice scientific calculator. Guys, you want a scientific calculator and you want to set it to operate in engineering notation. Engineering notation is scientific notation where it always gives you the exponent at a power of 3. Well, why is that interesting in engineering? We have milli somethings, we have micro somethings, we have kilo somethings, and we have mega somethings. And so it's nice when you use engineering notation because it puts it in those groups of 3. So let me get this and say, what is 5 divided by 330? It is 15.15 e to the minus 3 amps. All right. Now, really, anytime we use the current in math, we want it in amps, so it would be 15.15 e to the minus 3. But usually we would replace e to the minus 3 with milli. Okay, so we would say this is 15.15 milliamps. But now, if I were to use this in a calculation, I don't want to use 15.15. I want to use 15.15 e to the minus 3. Does that make sense? If it doesn't, ask me. Maybe I need to make a video on that if it doesn't make sense. And so here I have solved my first circuit analysis, and I calculated that if I put 5 volts across 330 ohms, I will end up with 15.15 milliamps. Now what you see is that when you're dealing with the Arduino, you're always going to be dealing in kind of milliamps or microamps. An amp is a huge amount of current. I mean, that would like kill you very easily. And so you deal with amps if you're doing things like wiring a house or power systems or things like that. Microprocessors and the types of things we're dealing with, we're always going to usually be way down in the milliamps. Okay, that was a very easy problem. Let's work a problem that is a little tiny bit more difficult. And I am going to try so hard to write neatly as I work this problem. In fact, I'm going to get another piece of paper here. Okay, here we go. So let's do a slightly more complicated problem. In this case, I am going to have 5 volts, and then it is going to go across 2 resistors. Okay, and so I'm going to have R1 is equal to 330 ohms, and R2 is equal to 100 ohms. Now, if you think of Ohm's law saying V is equal to I times R, well, what do? You've got 2 R's here. Well, the thing that you have to understand is if there's only one path through the circuit, if everything is in series, it becomes very, very easy. If it splits, if the current branches into 2 paths, then you've got to do some more complicated stuff. But most of the stuff that we're doing, it's in series like this, and so you can do it this way. This is how you deal with resistors in series. You can say the equivalent series resistance is the sum of the resistors that are in series. Okay, so the equivalent resistance is the sum of those resistances. So the equivalent resistance is 330 plus 100. The equivalent resistance is 430 ohms. Okay, now what you do is you redraw the circuit with that equivalent resistance. You would say that this circuit is exactly equivalent to this circuit. This is still 5 volts, and now this RS is what? 430 ohms. Now I want to calculate what? I want to calculate I. How do I do that? I is equal to V over R. And this would be our RS here. What is V? It is 5 volts divided by what is RS? 430 ohms. And so I have 5 divided by 430. That is equal to 11.63 e to the minus 3 amps. And then how are we going to write that? We're going to write that I is equal to 11.63 e to the minus 3 is what? Milliamps. And so here I have started my circuit analysis, but I'm not done because now I know this current here, and that's 11.63 milliamps. But now I've got to go back up to the real circuit, not the equivalent circuit. Well, what you can see is because they're equivalent, what is this current? It's exactly what we calculated. It is 11.63 milliamps, 11.63 milliamps. Okay, I am not done because what I really want now is I know the current through the circuit, but I need to know the voltage across R1 and I need to know the voltage across R2. And so the voltage across R1, I am going to call that V1. And V1 is equal to I times R, but which R? Well, R1, because I want the voltage across R1, so I use R1. So this is equal to 11.63, my current. And when I do a calculation, how do I put it? I got to put the e to the minus 3 for milli. So e to the minus 3 times 330 ohms is equal to, I will put in the calculator, 11.63 e to the minus 3 times 330 equals 3.84 volts. Okay, so if you look at this, I started with 5, I got 11.63 milliamps, and of that 5 volts, 3.84 volts dropped across the 330 ohm resistor. Now what do I need? I need to calculate the voltage across R2. We will call that V2. V2 is equal to I times what? Well, R2, because I want the voltage across R2, so that is R2. That is 11.63 e to the minus 3 times 100 is equal to 11.63 e to the minus 3 times 100 is equal to 1.16 volts. So I start with 5 volts. Can I zoom out a little? That's all I can do. Okay. So I start out with 5 volts. I have 3.84 volts drop across the 330 ohm resistor, and I have 1.16 volts drop across the 100 ohm resistor. Something very interesting. What is 3.84 plus 1.16? It's 5. Okay, so what you can see is it's almost like you have 5 volts to spend. You spend 3.84 volts across the first resistor, and you spend 1.16 volts across the second resistor, and now you're back to ground, and so you've used up all your voltage. And so what you see is the voltage around a loop is going to sum to what your supply voltage is. And that's kind of a handy thing to know, because after you do a circuit analysis like this, then you can actually check your work. You could do this same thing with 3 resistors. It's just the RS would then be R1 plus R2 plus R3. You would have your equivalent resistance. You would calculate the current, and then you would take that current and you could find the voltage drop across all 3. That works as long as there's only one loop in your circuit and everything is in series. Okay, now let's actually build this circuit. All right, let's build this circuit. With our kit, we have our prototyping board, so I'll put that there. I'll bring the Arduino in. And then if you look in your Elegoo kit, you will be able to find a 330 ohm resistor, and you will be able to find a 100 ohm resistor, and then you are just going to need a couple of wires. The interesting thing about this is I am not even going to hook up to one of the digital pins. I am just going to hook right up to this 5 volts that is over here on the other side, because I'm not even in need of switching this thing. I am just going to hook it up to the 5 volts. So I will get a red wire and I will put it into this 5V. You see the pin that says 5V? I will bring it over to, let's say, I kind of like to start in column 15 like that. And then I'm going to get my 330 ohm resistor. One leg is going to go in that column 15. The other leg is going to go in column 20. You understand it doesn't matter specifically what you do. It just matters that the dots, the holes in a column are connected. And so now I've got 5 volts to one leg of the resistor. Then what do I need? I need the bottom leg of that resistor to hook to the top leg of R2. So I've got R2 here. Do you think I should zoom this in to help you see a little better? Maybe so. Okay, maybe a little too far. I want you to see the whole thing, but as close as possible. Okay, so now I'm going to bend this nice, like that. Okay, easy to use. So now this is going to go also in that column 20 and then jump across this trench. Why do I jump across the trench? Because the columns above the trench are not connected to the columns below the trench. And so now I have made this circuit, right? Wrong. What am I forgetting? I have to take this column, the bottom of the resistor, that bottom of that R2, that bottom of that 500 ohm resistor, and I have to connect it back to what? Back to the negative, which is the GND, right? The GND is right next to, pin 13. Okay, so I hooked this up to 5 volts, so I don't even have to write a program. We do not even have to write a program. Why do we not have to write a program? We do not have to write a program because the 5 volts is always on. And so I have created this circuit, and what do I know? I know that the current through that circuit is 11.63 milliamps. Well, you might say, how do we know that? You know, shouldn't we check it? All right. The easiest way to check it instead of measuring the current is to measure these voltages across R1 and R2. And so let's start by measuring V2. All right. So what I have here is, and if you don't have one of these, man, if you're going to be in the, kind of in the engineering arena, you really, really, really need to get you a simple digital voltmeter. I think they're about 50 bucks, and I will put a link down below. This Mastech that I have is a really nice one, but it's a little older though, and so the versions that they have now are a lot better. Let's see, hopefully hopefully I'm out of the way here. And so what I do is I set this on DC voltage. It's the voltage with a straight line. And then what I have here is, you can see that I'm connecting the voltmeter through its leads all the way to these things so I can plug them into the board. So the first thing that I'm going to do is I'm going to go across the supply. So I'm going to connect to the same column as that red wire, which goes to 5 volts, and then the same column as, I do need to get out of your way here, the same column as this white wire. And look at that, I'm measuring the voltage that is coming out of the Arduino. Now what you know is we were expecting 5 volts to come out, and you can see that we have about 4.86. In this particular case, I think this meter is accurate to within a few percent, so probably we're not getting the full 5 volts out of this Arduino. We're getting more like 4.86. Maybe it's just the regulator in there is not perfect, but we're at 4.86 volts. So that means our numbers are going to be a little bit off because we did the analysis based on 5 volts, and so our numbers are going to be a little bit off. But can you see how I have this hooked up? And let me put it to make sure that you see it. I'm going all the way. This is one leg of the meter is hooked to the red wire, which is 5 volts, and this black wire is the other leg of my meter, and it is connected to the ground. All right, so that is how it's connected. And that we would have expected to be 5 volts, but it is 4.9. So the Arduino is not giving me exactly the voltage that I expected. Okay, now this lead here, remember, goes to our meter. This lead goes to our meter. And so what we are going to do is we are now going to measure across the R2. Okay, we're going to measure across the R2. So one lead of the voltmeter will go above R2 and the other one will go below R2. So if we look, this already is below R2 and this one needs to go above R2, and I will put it right there. And then what do we measure when we do that? We measure 1.16 volts, which is exactly what we calculated it should be, 1.16 volts across this R2. Now we want to measure across R1. So to do that, I would put the red lead above R1 and the black lead below R1 coming off of our meter. And so let's get those two leads. Okay, so here I have them. And so I'm going to put one above R1 by putting it in the same column as that lead, and then the same column as the other lead. So again, I put 1 in 15 and 1 in 20. And then what I am doing is I am measuring across R1. And if I measure across R1, I am measuring V1, right? I'm measuring V1. I'm measuring 3.73. What did I calculate that I was expecting? 3.84. This is about 1/10 of a volt off. Well, why is it about 1/10 of a volt off? It is about 1/10 of a volt off because I don't actually have 5 volts. I'm starting with 4.9, and so that's why we get a little error. The math and the physics work perfectly, but I'm not getting the 5 volts I anticipated, so this number is just a little bit off. Boom! We have done our first circuit design and analysis. We've built the circuit and we've tested it, and it is behaving as we anticipated. Okay, so again, if you don't have one of these nice digital voltmeters, look in the description below, and you can go ahead and get one, because they're really very useful. And in particular, when you're doing troubleshooting, you really need to have a volt meter like that, because imagine if your circuit's not working, you don't know why it's working, and you're sort of blind. Is it that, like, let's say one possibility would be a resistor is burned out or bad. Another possibility is your Arduino's broken and not producing a voltage. So you really need a voltage meter like that to poke around and understand what's happening on your circuit. Okay, now guys, leave this circuit set up, because we're going to be using this again in lesson number 10. What we're going to do is we're going to try to measure this voltage. We're going to try to measure this voltage not with a voltmeter, but we're going to measure it with the Arduino. And so far, everything that we've done with the Arduino has been to send signals to the pins. In the next lesson, we're going to learn how to read a signal from the pin. Okay, guys, does this make sense? Am I boring you as I'm trying to go a little bit more into the engineering? Let me know in the comments below what you think. I just felt like my first series of lessons was just kind of coding. It was just like copy what I'm doing and write the code. And I'm trying to get you to understand a little bit more of the math, a little bit more of the physics, and a little bit more of the engineering behind what we're doing. Let me know down in the comments what you think. Think about giving us a thumbs up. Think about subscribing. Hey, I've been getting a lot of comments and emails from people that you're not getting my notifications when I put a new video up. On the subscribe button, make sure that you click the bell. If you click the bell, you'll get notifications, and I am really doing a lot of videos here, so make sure that you click that. Think about giving us a thumbs up, subscribe, share this. This is Paul McWhorter. I will talk to you guys later.